Perfect. So, yes, explain about metallic hydride. Yesterday I asked you to go through it. Explain it. Metallic hydride. What do you understand from that? Yes? Anybody? Let me be specific with the name. Those who studied, please raise your hand. Very good. So, Charan, would you like to say something on this? Charan, can you hear me, buddy?
Yes.
Please explain about the metallic hydride. What have you? My dear, there are so many names: metallic hydride, interstitial hydride, and other name is also there, which is non-stoichiometric hydride. Yes. So please tell me any information about this. Yeah, go ahead.
Not exactly, sir. Just a heading, sir.
No problem. Whatever you understood from it, just a line or two.
So these are formed by D blocks and F blocks.
Yeah, right. And and
They violate the law of constant proportions. There's non-stoichiometric.
hmm,
And
okay,
non
They can be used as hydrogen storage because they can accommodate large amount of hydrogen within them.
very good. And all
They
right.
conduct heat and electricity.
They
Uh,
conduct heat and electricity, you are saying?
but less than their actual
yes, sir.
metals, which
Mm-hmm.
makes them different from covalent and ionic hydride.
Right. Very good. Very good. So, metallic hydride, what are the metallic hydride? These hydrides are formed by, please start writing, formed by metals of D and F block. They are non-stoichiometric in nature. They are non-stoichiometric in nature. Right? They are non-stoichiometric in nature. Then, then how does these metal actually form the hydride? So you remember a topic when I was discussing you about different forms of hydrogen, right? There I told you right, this is very simple layer structure, square layer, square packing I'm trying to draw over here. These small things These I am trying to show you about the hydrogen. Right? Although, excuse me, although this is not uniform in nature, right? Some will be there and some will not be there. We can't expect any uniformity over here. So these are formed, these hydrides are formed when metal crystal is heated at high pressure in the atmosphere of hydrogen. Right? So basically what will happen, suppose you are having hydrogen. So these are hydrogen. I have shown you at the top. Okay. So when you are going to heat it, they used to be present in the voids, interstices. That's why the name is given interstitial hydride. As you can see, the hydrogen atom is present here in this way non-uniformly. So if non-uniform representation is there and non-uniformity is there, so you cannot say that the formula will be uh, in a simple way. Like we have seen in the case of calcium and H minus, we have got the formula calcium H2 CH2. This is fixed. But here in this case, a very weird kind of thing will be there. Very weird. You'll be really surprised. You'll be really surprised to know that their formula are somehow like this also. Like vanadium. Example, if I have to quote, vanadium hydrogen 0.56. Can you imagine situation like this? Titanium is having a range, right? So I'll show you. You can see these two examples. 0.56 titanium TiH 1.5 to 1.8. Right? There is a range. It could be anything depending on the pressure. So like that, many example you can draft by yourself. So these hydrides are formed when metal crystal is heated at high pressure in the hydrogen atmosphere. So that's a very good way to store the hydrogen, right? Forming, or you can say absorbing hydrogen into the voids of the crystal, absorbing hydrogen into these voids makes it easier to store them, to store hydrogen, right? So whenever it is required, whenever you are thinking, you can heat it and you will get it back, right? Now many other question that is expected to ask over here. Suppose this is your parent crystal and this one is your parent crystal and this is your hydride form, right? This small one is hydride. This hydrogen, you can understand, these are H2, right? These are H2. These are metal crystal, and this is parent metal, and this is metal hydride. Although, my dear, you can see that I haven't shown any deformity over here, but it is not like that. Depending on the size of the metal and the condition, these can be deformed also, right? But few properties are more or less remains intact. Of course, it is going to make the changes out there. But overall, the major changes that we used to think, like calcium is a very good conductor of electricity, right? Electricity in solid state. But my dear, CaH2 is not, right? Non-conducting, you can say, in solid state. So the property is abnormally changed when you are going from calcium to calcium hydride. All right, right? So please make a point. Note, calcium is a good conductor of electricity, but CaH2 is extremely poor conductor in solid state, right? All right. Next thing is metal hydrides, because these were saline hydrides, no? Metal hydrides unlike saline hydride are good conductors of electricity, right? So you can add another word, that the properties of the metal hydrides are generally similar to those of parent metal, right? Identical, not identical, similar, right, my dear? Got it? So these discussion which I am doing right now is based on the old observation of these metallic hydride, right? So what did I make here? Important point over here is that these are present in the void. So indirectly, if these are present in the void, it is not going to disturb the crystal structure, right? As per the old observation. But recent studies in past, you can say a decade or two, it has been found that, because there are many advanced instruments that are present right now. With the help of those, the analyzing crystal structure has become much easier as compared to it used to be in the past. So recent study shows that the crystals of most of these hydrides are not similar as their parent element. So there are few metals still whose crystals are similar to the parent metal, and that is nickel and palladium. So if the question based on the recent studies they are asking, then you are supposed to answer. Otherwise, things are like this only. And again, I would like to tell you that the property which we are assuming, this is not valid. I mean, the properties that are similar, this is not valid for all the metal hydrides, right? It will vary. It will vary. It has been found the cases where if you are going to, hammer them, uh, they will have entirely different way of breaking it down, like brittle things. Whereas the metal, on the other hand, that is ductile and malleable, right? So these problems are there. Now let's talk about two important hydrides which I have till now I tried to exclude them. Those are the polymeric hydrides, right? Polymeric hydrides, very very important, right? So if I'll ask you, my dear, to arrange the following in increasing order of covalent character. I'll just symbolize it. Increasing order of covalent character, right? So the option I'm going to give you is the two parts you have to do, 1 and 2. Please go ahead with the beryllium hydride, magnesium hydride, calcium hydride, strontium hydride, and barium hydride. Likewise, LiH, NaH, KH, RBH, and CSH. So what would be your answer? Very simple. You're applying the Fazan's rule. Metal ion is differing. So polarizing power you can see, and accordingly you can answer. So the overall order will be that, sir, beryllium hydride is most covalent. Magnesium hydride, next number. Then the order will be like this. Do you agree? Yes or no? Any doubt in that? Fine. Guys, am I audible, right?
Yes, sir.
Thank you. So cesium hydride, the order will be here like that. So if I have to discuss about the hydrides, the nature of these hydrides, then if I'll ask you, could you please tell me the top three covalent hydride in this whole group? Top three hydrides. Top three most covalent hydrides. What would be your answer?
Lithium,
And
beryllium, magnesium.
Lithium is the one which you are going to consider at the top.
Yes, sir.
Beryllium,
And what about beryllium hydride? If I'll ask you which is more covalent, lithium or beryllium?
beryllium.
Beryllium.
Hmm? Beryllium hydride.
Yeah.
So you can, yeah. So on the top, if you will discuss, the answer would be beryllium, magnesium, and to some extent you can consider even lithium hydride. Okay. So most covalent out of these all saline hydride, the most covalent hydrides are beryllium. BeH2 and MgH2 have good amount of covalent character. The moment I said good amount of covalent character, it means there is a chances of polymerization. That's why BeH2 exists as polymeric. Even even my dear magnesium also, right? Even magnesium also occurs in that way. But the structure is temperature dependent. For magnesium hydride, the structure is temperature dependent. MgH2 also have similar structure you can write rather than writing poly. Structure, but that is temperature dependent, right? So I hope that magnesium should not be asked in that domain, but let me just tell you. So this beryllium hydride, I told you the structure. If you are going to simply think about the monomeric beryllium hydride, then monomeric is like this, BeH. Now if you'll think about its hybridization, it is sp. So having two vacant p orbital. So obviously in that way it is electron deficient, yes or no? So I am going to just make a replica out of it. Just give me a minute. Right, my dear. So I'm going to show you how does it look like in terms of orbital. Right. So what happens? These two electrons now, because it is already having 4 electron, so it tries to overlap in a very special way, and this special way is possible uh, in very few cases. It is not possible with all of them, like the cases of beryllium. Even as I told you, at certain temperature in the case of magnesium, then we have such overlap in boron, then we have such overlap in case of aluminum. So these hydride have this special bonding. I will tell you. Let me first draw the orbital picture of that. So orbital wise, if I have to draw, can I draw like this? That okay, this is the hydrogen. Yes or no? Here I am writing H, but please understand that is showing the nucleus of hydrogen, right? This is the overlap. How many electron do we have over here? 2 electron. So ideally, this is the situation, right? Ideally, this is the situation. So for few cases, I will show you. The rest you can draw by yourself. Now, what happens because this is highly electron deficient, so it tries to manage by special way of overlap the orbitals of beryllium used to take the electron like this. Can you see this? A very special way of bonding. Three of the orbitals have overlapped at a common point, and you can see that these 2 electron now belongs to these three centers. So that's why, because of this nature only, we used to name this as three center 2 electron bonding. And you can see the overall shape that it is going to generate is like a banana. This overlap, this bonding is going to, it is said to be banana bonding. Right? So one one of them I showed you. In the similar way, you can draw all of them. You can draw all of them. Let's make the overlap possible. Take the hydrogen over here, and here dot dot dot, the structure will continue, right? Like that, my dear. I don't want to show all the orbitals, so please understand it is going to happen in this way. Now, interestingly, after this, just dotted line doesn't mean that this is not a bond, right? You can draw by yourself. I will just make a proper bond. Okay, and so on. It will go ahead in the same way. Right. So if I'll ask you, what is the hybridization of beryllium now? Tell me. Hmm? What is the hybridization of beryllium? Come on, guys. Guys, am I audible? Hello. Hmm. What's the hybridization of beryllium in this structure?
SP.
Sp? No. Right now, because of the 4 bond formed by one beryllium atom, the hybridization is termed as sp3. And the moment it is sp3, the rings are alternate. I means one in plane, other in perpendicular, other in plane, other in perpendicular. The consecutive rings are perpendicular to each other. Right? These two rings are perpendicular to each other. This is this ring. The other one will also, I'll show you like this. Please understand, rings are perpendicular. Successive rings, consecutive rings. Alternate ring, alternate rings are in same plane. Right? You can write down like this. What do I mean by that? I mean to say that these are in same plane, but these two are perpendicular. Perpendicular plane. Okay? Perpendicular to each other. Right? These two are perpendicular planes. All right, everyone. Understood that? So the hydride of Be hydrides like BeH2, MgH2, B2H6, AlH3 solid, right? H3. And the other boron hydrides are have they have 3 center 2 electron bonding. So now the next question comes that, sir, will we get these three center two electron bonding only in the case of hydride? Don't we have other cases? Yes, we do have, my dear. AlCH3 whole thrice when undergoes dimerization, that means Al2 CH3 whole 6. Even in this case also we have that bond. Here also the same situation is there. Sorry. There is pair of electron in this. You can look around that we have such sort of bond even present over here. You can see this is acting as a bridge, right? So bridge bonding is also, you can name them as bridge bond. Right? All right. So now we are done with the uh, hydrides about all three. Now the next question is, sir, as you told while teaching this metal hydrides, that most of the elements, you did not use the word that all the elements. So could you please tell me the list of few elements which do not form hydride? So one you can understand by yourself. That's so simple. Can you tell me which one?
6, 7, 8, 9.
Noble gases, right? That is the easiest one. You can say, sir, noble gases will never form na hydride. Yes or no?
Yes, sir.
Noble gases will never form hydride. Hmm? So in that particular case, so that is anyway excluded because noble gases do not react with most of the elements. So there is a term called hydride gap, right? Few element in periodic table, okay, do not form binary compound with what?
Hydrogen.
They are termed as hydride gap. So what are those elements? So chromium, right? This is the group element. Mn, this is the group element. Thereafter, Fe, Ru, OS. So my dear, these are the elements which I am trying to highlight. Don't form any hydride. And it's termed as these gaps, these gap are termed as hydride gap, right? This is referred as hydride gap. All right, guys. What are these? These are hydride gaps.
Sir, once can you show the previous page? Yes, sir.
Right. So I am discussing just based on 3D, 4D, and 5D only. There might be few metals here and there which are not
The
forming,
ninth,
but these, sorry,
ninth,
Ninth group.
ninth group. Which one you're talking about? Ninth means this one you're talking about seventh, and then eighth and ninth. Acha, yes, yes, yes. I forgot. Even that will also be the uh, that will also be the part of this gap. Please take that group as well. Guys, I'm not able to put on my videos. Is it the case with all of you? You guys can on, right? I don't know what's the problem here.
Yes, we can.
All right, there is no issue anyway.
Maybe you didn't give permission to the apps.
Might be, might be. So yeah, so so you have noted it down.
Yes.
All right. So this was the discussion related to the binary compound. Now, can you please tell me the other possible reactions? Yes, the other possible reactions of this. Acha, if I'll ask you one thing, can you tell me the thermal stability order in the case, because that also we need to revise here and there. Can you tell me, because these points I'm not thinking to give you in notes, because once already discussed means you are supposed to apply, but still you tell me, what do you think about the thermal stability order in this case? In the case of lithium, sodium, potassium, rubidium, and cesium. Hmm? Thermal stability order in this particular case. Or the relative stability order, you can say. Hmm? Tell me, which is most stable? Lithium, sodium, potassium, rubidium, and cesium, which is most stable?
Lithium.
Lithium is most stable, right?
yes, sir.
All right. Okay. I was actually thinking here about these two groups, and I think one of you said about nickel, the group of nickel, right? But I personally, I'm little skeptical. I'm not very sure about nickel, because if I look at the
Not
example,
nickel, sir.
yeah,
Cobalt.
I'm having the example of acha, right, cobalt, sorry, not nickel. Because with nickel we used to have this thing now, NiH2 is a very good reducing agent, right? So that is forming hydride, so not nickel. Yeah. Right, it is cobalt. You can add that. I was missing that point. Right, so please add that. Do you remember this periodic table, especially D block, block wise, group wise, sorry? Do you remember these metals? Otherwise, you will be in trouble. Okay, try to memorize this one by one by one by one. You try to do that. Okay, so these are referred as hydride gap. All right. Okay, everyone. So now let's talk about the reactivity of the hydrogen. Uh, the general hydrides I have already discussed with you. Now, can you tell me, can you quote few reactions? Can you quote few reactions?
with halogen.
Yes, with halogen. What will
With
happen?
oxygen, hydrogen.
Chemical reactivity. Chemical reactivity of hydrogen gas. Yes, please tell me. First of all, whenever you are looking at the reactivity, the first point that you should always think about is, see, one way is just start reading the thing and try to mug it up in its own way. The second way is give a thought on this. Like, as you know that hydrogen is having a very strong bond, strong covalent bond, non-polar in nature, non-polar in nature. So you can say that it is not reactive at ordinary temperature, right? So it does not react with most of the compound at room temperature. You can't expect that this will react normally with anyone, right? But yes, suppose if the reactivity of the species which is going to interact with this hydrogen is really high, right? In that case, it reacts, right? But here you can write, but with halogens, with few of the halogens, not all, like F2, it reacts even in dark, right? It even react in dark. Right. So you will ask there, sir, why you wrote all this point like strong covalent bond, non-polar in nature. So suppose if I have to break this hydrogen into H plus H, so what do you think that the temperature should be? So my dear, if you read the book properly, you'll figure out somewhere around 5000 Kelvin, somewhere around that temperature, you are going to make them dissociate up to 95%. Right? So you can imagine the amount of the temperature that is required. Whereas the fluorine, on the other hand, chlorine, bromine, they used to break at the room temperature itself directly. Light, if you are exposing with the light, they will break down. They are so reactive because one of the weakest bond that we have among the element is there, that in case of halogen, right? So just for your knowledge only, I'm putting in this. At nearly 5000 Kelvin, it breaks up to 95%, approximately 95%, I'm telling you. Just for your knowledge only. So you can't think that, okay, hydrogen will react with anything very easily, right? So let's start writing one by one. So at first I will discuss reaction with halogen. Reaction with halogen. So reaction with halogen. As you know that halogen, since halogen poor bond energy, so the reaction with halogen occurs at relatively, not low temperature, relatively low temperature as compared to the other elements. So if I have to generally represent, H2 plus F2 will form 2HF, highly exothermic. H2 plus Cl2, again, sorry, HF, right? 2HCl, that is also exothermic. H2 plus Br2, 2HBr, delta H is again negative, but low value. But H2 plus I2 does not form in the forward direction, delta H positive. So formation of HI is not favorable, my dear. Right, so I should make a comment over here. The reaction with fluorine takes place in dark. Right, in dark. The other point is chlorine react only in the presence of light. Right, bromine reacts at 573 Kelvin. 573 means how much in degree centigrade? But I2 reacts reversibly at 713 Kelvin. And that too in the presence of platinum. in the presence of platinum catalyst. So you can say that this is not a very favorable process, right? So it is not so easy because of this platinum catalyst, some sort of reaction is happening. Otherwise, these three are quite favorable, and you know that hydrogen reaction occurs at very low temperature, and that too in the dark. You can understand because of exceptionally poor bond energy. So this was probably the most reactive nature of uh, halogen, which is forcing this hydrogen to react. Okay. Now, next possible reaction, the next possible reaction which relatively occurs after this. This was the most reactive thing. Then next thing is reaction
Oxygen.
with, yeah, very good. Reaction with oxygen. Now, can you guess that if I am going to mix it normally, will it react? H2 plus
No, sir.
O2, if I'll mix, will it form water? Huh?
Not at low temperature, sir.
Suppose if I'm taking at room temperature, even if I'm taking at 100 degrees centigrade, what's your sentiment says? So see, if you are not, aware of this, that's why I was giving you these points to understand that reactivity is a matter of the bond energies which are participating in this reaction. For breaking H2, we need that amount of energy. So for that, you are supposed to take it. Either some other thing will be there, like these things have extra capability because in the presence of light, they used to break down into radicals, and these radicals are having unpaired electron. They are extremely reactive, and because of that, it is possible with halogens to react even at low temperature. But still, as you can see, for bromine and iodine, the reaction nature. For H2 and I2, right, what can you expect here? Although the nature delta H, if you'll talk about, this is reported as somewhere around 285, 285, approximately 285 kilojoule per mole. Such an exothermic reaction, you can look at here, it is so exothermic, but still does not occur at room temperature. Hmm? Tell me. Tell me, guys. Yes, even such an exothermic reaction, what is your guess at what temperature they should react? They will not react at room temperature. Even if it is so exothermic, the reaction will not take place at room temperature. Will not take place at room temperature. Hmm? How much? How much can you expect? So if you refer a proper standard book, for a mixture of hydrogen is to oxygen, H2 is to oxygen, if you have taken in 2 is to 1 ratio, then this used to ignite at a temperature of 570 degrees centigrade, and that too also requires some initial spark. That too also requires some initial spark at this temperature also, right? So this is the temperature at which they are going to react, and if you are going to use the catalyst, then they may react at even lower temperature, right? In the presence of catalysts like platinum, like platinum black or palladium, the reaction takes place at ordinary temperature. Understood, now? Okay, so the reaction of hydrogen is not so easy that you are going to get the product just every time you refer the bond angle. Now let's talk about another thing, reaction with this was second, this was second. Let's talk about the third reaction, reaction with nitrogen. What will you expect? See, with oxygen still we have some advantage that oxygen is a diradical. Do you guys agree with my statement? It is a diradical, means it is having two unpaired electron. Do you guys agree?
Yes, sir.
So still that O2 is having tendency to react with oxygen. Fortunately, that is the reason why even at 570 also this thing happens, right? Now think about the reaction with nitrogen. Oh my god.
Both are inerts.
Right, right. Hydrogen, you can't expect this reaction to happen. It requires extremely high temperature. Right? It requires extremely high temperature. So for making it possible, in the uh, at the time of World War One and World War Two, there were researches going on to produce ammonia cheaply because the there were researches going on that anyhow by hook or crook, let's use certain chemicals which can kill the opponent in the form of poison, right? If it is spread in the form of poison. You will be knowing one scientist very well. The name of the scientist is, can you tell me? Who gave an excellent method to prepare ammonia?
Haber.
Yeah, right. Haber's process. That very famous reaction is known as Haber's process. 3H2 plus, these are all gases, and it forms ammonia. What is the catalyst used? This is also exothermic. ammonia is mainly produced by Haber's process. So imagine how difficult this reaction was. That's why we are giving so much importance to the scientist who actually made it possible relatively at the condition which we can achieve. Hmm? Do anybody know that which are the catalysts used over here?
Iron.
Iron, sir.
Huh?
Iron, sir.
But it is modified. Earlier it was iron as a catalyst. Later on it is modified. There are others also, but this is the case. And still this reaction is reversible. This is not 926, this is 92.6, guys. Please make it very clear. Kilojoule per mole. Can you just think about this? Okay, and you'll be really surprised the intention behind producing ammonia was not in the welfare of the people present around the world, but rather what was the purpose of producing ammonia? To use it in warfare, to use it in war. And you know that because of this particular reaction and making this ammonia feasible at relatively achievable condition, Haber was nominated for Nobel Prize. You know that? And many scientists across the country, different countries, they raised the concern. They opposed him strongly. Except, forget about the scientists across the globe. His wife was also one of the person, you can say, who was also a very good chemist, and she also resisted this whole uh, you know making of this ammonia in this way. So there is a history of Haber's that his wife committed suicide. His wife committed suicide just to because she was not very much agreeing with Mr. Haber about the usability of this ammonia. But anyway, in what context this ammonia and why he was awarded Nobel Prize or why he was nominated for Nobel Prize was not the case of this usability of ammonia in terms of to form a poisonous gas. He was called because the production of ammonia reformed the way people were doing farming. Across the globe, it was really difficult to produce, uh, you know, to produce crops at a good yield. The process of fixing ammonia is not very easy. The process of fixing nitrogen from atmosphere is not very easy process. It takes a lot of time. And two, unless it is mixing with the soil, it is not going to participate in the growth and development of the plants. So this was one of the most wonderful way by which this ammonia is produced. Thereafter, urea and many other things are produced from this, right? Fertilizers, which are greatly used across the corner to increase the yield of the crops. So you can understand the intention was not right, but again, the uses of these chemicals depends individually, right? He started making this. He was day and night working out for the production of ammonia, not to actually uplift the humanity, rather to destroy it. So that was the reason why most of the scientists across the globe opposed, because the Nobel Prize is given to the people who have right intention behind discovering something. Okay. But fine, history is history only. So ammonia is produced by the Haber's process, and this is how. And still, still it requires good amount of temperature. Still the temperature is T is equal to, I will tell you, somewhere around 600, 673 Kelvin, and pressure of nearly around 200 atm. Still it is not easy. So you can imagine, in the presence of the catalyst also it is happening at this temperature. Then you can imagine that reacting H2 with N2 is almost impossible, right? So that's why this is recognized as one of the most important reaction. So please remember this. This is really, really important. Now, next reaction is reaction with the metals. As I already told you, reaction with the metals. Right. So suppose if H2 is there, M is metal. If it is alkali metal, it is going to form like this. High temperature. Alkaline earth metal will form MH2. You can write down these phases. This is solid. This is also solid. This is gas. You can write down. Alkaline earth metal. Right. Note, very, very important. BeH2 and MgH2 can't be prepared directly by heating metal with hydrogen. So what's the other way? There are other ways also by which it is prepared, like beryllium chloride when treated with hydrides like sodium hydrides, NaH, then you can expect this BeH2. You can expect with LiAlH4, you can expect this BeH2. So there are many such reactions which will take place. So basically it is the transfer, right? It is the transfer. So it is indirectly prepared by beryllium chloride, not directly. I will discuss this point once again once you will be there in the S block. But right now, just till here you just consider this, right? The other possible reaction, if you'll be talking about the other possible reaction, many other reactions are there, but I'm not so much interested in that. Some metallurgical reaction, some reaction which occurs in metallurgy and which are important for us is this. Please make a note. Reaction with metal oxides. But please understand this. Metal oxide whose metal is less reactive than iron. Less means these metals, right? In electrochemical series can be reduced to metal by hydrogen. Less reactive than, they can be reduced. Means H2 is going to make them Now you will say, sir, don't you think that it is very weird? Technically, it should be these only. But answer is these reactivity series is obtained in aqueous medium, my dear, in water. But the reaction which we are actually doing here is occurring at high temperature without water. Direct metal oxide is heated with hydrogen, and that too at high temperature. Right? So this is very, very important. Less reactive than iron. Please make a note on that. So hydrogen acts as an reducing agent. It reduces metal oxide to metal, but for the metal which lie after iron, means not above, below iron. You can highlight that point. And rest of the reaction you already know, the reaction of H2 and Cl2. Most of you already know, right? Fine, everyone. So now we are done with the reaction of hydrogen. Okay. Now what next? Hydrogen we are done. About its reaction, properties, uses, we are done with it. Now what next? Hmm? What next?
Sir, we should note down Cr2 3 CH3 also. Sir.
Which one?
Reaction of H2 with CO also.
With these or with
With
carbon?
CO.
Acha, this one. Ah, yes, you can note it down. Reaction with CO of H2 may produce various things depending on the catalyst you are taking. With nickel, it produces methane. With copper, it produces this thing, HCHO. With chromium oxide, it produces.
Okay.
Sir, providing heat is needed. No, sir.
Yeah, of course, in every reaction. That is understood here. Hmm? Note it down.
Yes, sir.
All right, guys. Okay. So now we are done with the reaction of the hydrogen. What next? What are the next thing that in the order? What is the topic which are still remaining? Are you guys reading NCERT on daily basis, guys? Are you reading NCERT? How many of you are?
Then you send
No.
NCR PDFs.
You don't have? You guys don't have? Rare. Okay. I will share, but how many of you are reading? That you should have asked on the day one when I gave you the reading thing, right? Every day you are supposed to read at least 6 pages. Minimum of 6 pages, I'm telling you. All right. Okay, guys. Very good. So the next thing which is there in the pipeline, what are the things that are left till now? It is about the water and D2O comparison. Then I will discuss here about hard water. Once this is done, qualitative treatment also thereafter. The last point will be H2O2, hydrogen peroxide. I think that will be the final thing associated with that. So these two things are left. So let me start today about water. Now you tell me about water first, whatever you know, right? Whatever you know about this water and hard water. Sorry, heavy water. What is heavy water, guys? What is heavy water? Water means normally H2O. Heavy water means D2O. Understood, na? Heavier isotope forming water is. Why didn't I discuss about T2O? Because tritium is radioactive. Yeah. You'll think that you are studying the property of T2O, but you will be studying the property of mixture of T2O with helium. Right? You remember now that this tritium undergoes decay and it forms helium. You remember through beta emission? Yes or no?
Yes.
Yes, sir.
All right. So just normally think about water. Here there are so many things related with water. Normal water molecule, you are supposed to know everything about water, right? Because water for us is more than a molecule. For us, water is an integral part of our life. In fact, water is life for us, isn't it? A human body is having, if
Yes.
I'm right, more than 70% of water. Most of the thing which we used to eat is having a great content of water. So we are supposed to read as much property as possible about water. So some very basic thing is melting point. We know that 0 degree centigrade. Boiling point. These are very basic things. This you are supposed to know. 100 degree centigrade. Specific heat capacity. Huh? Tell me. Specific
One
heat capacity.
calorie, 1 calorie per gram.
Right. Specific heat capacity. One calorie per gram per calorie. Right? Density. When I'm saying density, I'm
1000
talking
per
at
meter.
4 degree.
One.
4 degree it is 1 gram per ml. Isn't it? Molecular weight, every one of us knows about it. Isn't it? Now we should know few more things. Like when H2 combines with O2, these are gases and forms just 1 mole of liquid water that at room temperature, the enthalpy change associated with it is known as enthalpy of formation of water. Remember, I discussed this enthalpy of formation of NaCl ones. You remember that? And this value is, yes, anyone who knows this
Minus
value?
285
Minus,
kilojoules.
yeah, approximately minus 285 minus 286. Approximately minus 286 kilojoule per mole. So this is enthalpy of formation.
So that divided by 2.
Why? Why it should be divided by 2? Tell me, Baba, why it should be divided by
Because we
2?
are taking fractional.
Hmm? Check it out this value and tell me. Look at very carefully. Just water. When I'm saying the enthalpy of formation, I need to ensure the product has 1 mole. We need not to be worried about the reactant. Right? So as I told you, the formation is defined. You remember NaCl ionic compound formation energy was associated with formation of 1 mole of solid from their constituent element in their standard form. You remember Na plus half Cl2. So here also we are using the same thing, right? So if you will do double, you have to multiply with 2. 2 times here and then it will be
So
1
in
and then
NCRT, they gave, if we multiply with 2, they gave minus 286.
multiply with 2. They gave this value as 286. You just check that, okay? You just check that. If it is like that, I will just make a change. For now, I will
I
keep
don't know,
this.
sir, but with me, I have an old edition.
All right, all right. So for now, I will keep this. If the stoichiometry is already multiplied with 2, then I have to change this value. For now, let's keep it this only, okay? Anyway, don't worry. They're not going to ask this value in the examination. Don't worry at all, okay? But these are very common things which we are supposed to know. All right. And the other things also you already know about the ionic product, Kw. That also you know. Okay. So I think I need not to tell you about the importance of water. You already know. You can describe in many lines if it is required. I think we should quickly compare the properties of water with D2O. You remember once I compared the property of H2 with D2 and T2. You remember that? So tell me, in that particular case, which one, the H2 part or D2 part was dominating mostly?
D2.
Hmm?
D2, sir.
D2.
D2.
So like that here also, for most of the property things will be like that. Again, I'm using the word for most. Not all the property of D2O is dominating. So you can have a quick comparison between H2O and D2O. Whole list of table, I will highlight wherever it is required. I don't think I need to tell you about molecular mass, but if you want to write, you can write. Right, H2O and D2. Molecular, excuse me, molecular mass. It is, 18 approximately, and this one is 20, that. I'm not writing in exact. So now let's talk about melting point. Whenever I'm writing MP, it means melting point. Let me write all of them together. Melting point, then boiling point, then enthalpy of formation, enthalpy of evaporation, enthalpy of fusion. F stands for fusion, V stands for evaporation, right? Temperature at which the maximum density occurs. Density ionic product, represented by Kw. Solubility of NaCl per 100 gram of NaCl, which is an ionic compound. If you look at all these value, my dear, melting point, it is 273 Kelvin, and this is 276.8 Kelvin. You can see that it is higher. Boiling point 373 approx. This is 374.4. Enthalpy of formation, it is minus 285.9. This one is minus 294.6. Vaporization, it is 40.66. It is 41.61. Right. Enthalpy of fusion, the value is reported, it is 6.01. This value is not reported. 276.98. Sorry, I need not to tell all these points. Then the density is 1, and this is 1.1. 1.10. The next thing is point dielectric constant. I wrote or not? I did not write now. Dielectric constant. Just representing the value so that you can have an idea. Viscosity and dielectric constant. So interestingly, if you figure out, you will be finding that the only one property which is dielectric constant of water is 35.9, and this is 30. So I am going to highlight this. So except this one, rest all the property you see that D2O is dominating. Ionic product Kw, when it comes, then it is 10 to the power minus 14. And this is 3 into 10 to the power minus 15. Okay, here also you can consider. This is also one of the important thing. Because dielectric constant is more, so expected ionization is a bit more. Dielectric constant I already gave you 78.39. So any property which is left, yes, solubility 35.9, and this is 30.5. Anything which is related with the polarity, even you can expect this also. Viscosity 0.8 and 1.1. Right. So you can see that except these, most of the property of this D2O is dominating. Heavy water is dominating, whether it is molecular weight, molecular mass. So melting and boiling point is proportional to that. You can see that how this is varying with that. Formation energy, it is 285, it is 294. Vaporization, it is higher. If the data is given, you can expect even fusion is higher. Density you can see is higher. Right, viscosity you can see is higher. Three things: ionic product, solubility of NaCl, and dielectric constant. These are quite correlated with each other. These three are only higher for H2O. So please make a note there. Most of the properties of D2O is dominating. But dielectric constant, ionic product, and solubility means ionic compound of what H2O is dominating. So I have highlighted these properties. I hope you have already noted it down. Please make a note on this. Note it down, guys. Everyone, note it down.
Just can you scroll down, sir?
Done, everyone? Yes or no? How many of you are done? Raise your hand. Fine, 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 fine. All right. Now, coming back to certain reaction of water. Tell me the nature of water. If I'll talk about reaction, what's the nature of water? You tell me. Do we need to study about the preparation of water? It's already present here, all around us. We need to simply collect it, right? So we are not supposed to read that. Let's talk about the reaction. What are the reactions of water? First thing, reaction and its uses, right? First thing is, water is an excellent solvent for most of the reactions. Easily available, cheaply available. So most of the reaction involving what? Polar molecules. Involving polar molecule, right? Next, because of its high dielectric constant, polar molecule and ionic solids. Because of its high dielectric constant value. Next thing is, next point you can make a note over here. H2O because it is having a lone pair can act as lone pair donor, isn't it? And any species which is lone pair donor is known as Lewis space. Right, everyone? So many of the reaction where an acid is involved, like whenever we are involving an acid, like even in the case of HO, C double bond O, CH3, very simple acid. Here also it is donating its pair of electron to the proton. It is donating here, this is breaking the bond. So you are going to get H2O, basically H3O plus. O minus C double bond O CH3 aqueous I should write because this negative ion will also be surrounded. This one I should write as next reaction you can expect is this is an acid. Reaction with metal. So if you are going to treat it with metal, so what sort of reaction you are expecting here?
Liberate hydrogen.
Liberate hydrogen. That's true. It will liberate hydrogen. With different metal, obviously, it will react differently, right? It may require high temperature, low temperature, but it is going to release. And you know that metals above hydrogen in electrochemical series will react with water at different temperature to produce hydrogen gas. So you know most reactive lithium to cesium plus water. This is going to form LiOH dot 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 to CSOH plus hydrogen gas. Very, very important point here. Sodium reacts vigorously. Water. But lithium slowly. Isn't it interesting? Sodium reacts vigorously with water, but as per the electrochemical series, you remember where does sodium come? Can anyone tell me the logic behind it? See, the sodium, as per the electrochemical series, comes over here. Lithium is most reactive as per electrochemical series. But why do we have such thing with this? That sodium reacting vigorously.
Sir, electropositive current.
Hmm?
Raising accuracy.
Anyone? Guys? Hello? You guys are there?
Yes, sir.
That's great. So, could you please throw some light? Could you please tell me? Hmm? So, this is,
Electropositive current.
I don't agree with you because that is whole soul decided. What is electropositive? If the reactivity series is like this, why you are focusing on electropositive? I'm not very convinced with your answer.
Sir, is it because of polarizable?
So polarizability is a bad thing or good thing? I think it's a good thing. More polarizable, more hydration energy will evolve, more energy will evolve. Hmm? Fine, guys. Keep thinking on this. So you can expect that even at cold water, they are going to react. Iron reacts with steam. Then it produces hydrogen gas, right? and plus oxide of iron. Isn't it? At red hot condition we have. So depending on different temperature, so like this reacts with cold water, they react with extremely hot condition. So like that you can expect. So reaction with metal. Reaction with metal oxide. So what can we expect? So there are, if I should classify, I can classify the metal oxide.
Sir, once can you show the previous page?
So it will simply form LiOH and cesium hydroxide. Aqueous, when I'm saying aqueous, please understand cesium ion is surrounded with water plus OH ion is surrounded with water. Layer of water is there. Okay, so these oxide when dissolved in water, they form hydroxide. Very very few oxide water, soluble in water, and this is one of them. You know, beryllium oxide, magnesium oxide, calcium oxide. Radium I should not discuss. Water does not dissolve. Water sparingly soluble, means very light amount. They are soluble. They are soluble. Except this, my dear, you can't expect the solubility of Al2O3, zinc oxide, chromium oxide, iron oxide, nickel oxide, right? Bismuth oxide, tin oxide. They can't be oxidized. They can't be not soluble. So most of these hydroxides are insoluble. These are very rare, as I told you. These are soluble. You should mark them. These are the ones which are soluble. Rest of them are insoluble in water. And a day before yesterday, I have already spoken about the amphoteric, neutral, and acidic and basic oxide. Yes or no? Did I tell you?
Yes, sir.
Fine. So that is it for today, everyone. So I think most of the thing I have covered over here, and yeah, you can even expect the non-metallic one, non-metallic like Obviously, N2O, NO, and CO you can't expect. Neutral oxide. Water, they are all gas, na? Not soluble. Okay, the other acidic oxide like SO3, P4O10, P4O6, right? Like uh, the other non-metallic oxide, they are soluble in water. And if it is in +6, it is in +5, it is in uh, 6 by 3. So +3. So you are going to get corresponding acid H2SO4 +6, S3PO4, my dear, +5, and S3PO3, which is +3. So non-metal oxide, acidic oxide, when dissolved in water, form acid. Gives acid with gives acid, simply acid. All right. So I think that's enough about their oxide. Uh, Similarly with the hydrides, if you think about like Ionic hydride, so I can endlessly, speak about this with water, like NaH plus water will be forming NaOH aqueous and hydrogen gas. So like that, I can speak about it endlessly, my dear, right? Never-ending reaction. Even even B2H6 can be decomposed by water, and you will be getting hydrogen gas in this case also, and H3BO3. This is covalent hydride. Ionic hydride will give, but covalent hydride having hydrogen in -1 state. So we have situation like this, B2H6, that also donates hydrogen gas. Is that clear? So that's it. I would like to stop the lecture at this point. And
Sir,
yes.
will
What else?
post NCRT material.
NCRT, I will definitely share, my dear. Definitely, I will share. Okay, that's all. That's all, everyone.
Sir, yesterday's notes.
Notes.